Welcome, everybody. This is the final meeting for the year for Tucson Astronomy's Fundamentals Interest Group. Tonight, I see one new name that I don't recognize. And so for those who are unfamiliar with this meeting typically has two presentations. We have a main topic, generally, which I will be giving tonight on galaxy classifications. It'll be the first part of two because I had so much material I couldn't fit it all without being like a 2 hour presentation. And then a second topic, which has been either in the past a constellation or more recently an astronomer of historical importance that we present on. And that tonight will be given by Doug Smith, who will be presenting on Harlow Shapley. And Doug, if you want to go ahead and start us off tonight, you should
Hey, can
have.
you start?
Can I start?
Yeah.
Sure. Certainly can. Do not mind at all. You remember where some buttons are. And get rid of subtitles. Can everyone see my screen okay?
Yep.
Cool. So, as I briefly mentioned in the introduction, this is going to be a presentation that gets in two parts. Tonight, I will be talking about galaxy classifications before Hubble, about which you'll see why that's a little bit of a misnomer, you know, here briefly. And we will then dive into all about Hubble's classification system, which encompasses the four main groups that many people are likely more familiar with. And then the next presentation, which I think I'll be giving in February, depending on the schedule, will cover on some specific subclasses um, of galaxies that some of which you may be familiar with, like for example, quasars or blazars and dwarf galaxies, and others that you are likely very much not familiar with, and where these individual subclasses fit in the overall scheme of modern astronomy. So we first begin with our good friends, the Herschel family. Prior to the 1920s, with Hubble's landmark work, galaxies were not actually recognized as a distinct entity per se. They were just classified as another type of nebulosity in the night sky. This was predominantly because, we were unable to precisely determine just how far away many of these objects were. The primary method for determining distance at the time resolved along what's known as parallax, which, if you take a finger in front of your eye and rapidly blink between your left and right eyes and you see your finger move, that's the general gist behind parallax. So, without knowing any distances, we all just assumed that these were nebulosities within our own galaxy. And another contributing factor to some of this was that we didn't really have photography up until the 1880s, with some of the first forays into astrophotography. Everything an astronomer saw, every diagram they wanted to describe, they had to hand transcribe for the printing press. And it was basically whatever that astronomer saw through an eyepiece, which, as many people will be familiar with, can very much change depending on the person who's looking through the eyepiece, as well as because of defects within their eyes, such as astigmatisms or maybe poor vision, and a variety of other factors. So this visual evidence was sometimes not wholly reliable. This here is one of was likely one of the first sketches of a galaxy. This was drawn by John Herschel. And this is the now very widely popular galaxy known as the Whirlpool, Messier 51, which is located in Ursa Major, uh, representing what was then probably the just a detailed image that he saw through the eyepiece at the time. And as you can clearly see how unreliable this is as we compare this to modern photographs and even some of the optics that we have access to today for visual observing. This does not look like the Whirlpool galaxy at all that some of us are more familiar with. And so during the course of assembling what has since become the NGC catalog, John and William Herschel uh, basically set out, well, didn't really set out, they ended up making a very rough binary classification system where they separated things out into galactic and non-galactic nebula. This is a bit of a, it sounds a little bit odd here, just from the name of galactic versus non-galactic. Since we didn't know what galaxies were at the time, we just knew that the Milky Way was a galaxy. And so this naming scheme presented itself because they just found a lot of certain types of nebulas along the central disk of what we see as the Milky Way, and others that were randomly distributed everywhere else. Hence this separation. And one of the initial insights into what would eventually become a classification system is that they just noted there was a very large variety to shapes between the non-galactic nebula specifically, from ovals to ellipses and so on. And going on this is as they worked through assembling their massive catalog, they would develop some minor classification schemes based on size, shape, and how dense the center regions, or what we now know as the galactic core, is, and separated them out that way. And it took a while, but basically until the early 1900s, or sorry, misspeaking here, jumping ahead. As the Herschel went through and assembled their catalog through Herschel's giant 40-inch scope that they built in his backyard, they we jump over to Ireland, which would build what was for many years the largest telescope in the world, in of all places Ireland, which you don't really associate with good observing weather. This was a very significant telescope. I can't remember if it was like a 2 meter telescope at the time using mirrors. And over the next 40 years from its initial commissioning, astronomers based out of Parsonstown would develop a very sizable collection of hand-drawn nebulas and would kind of, and along with the Herschels, developed a semi-classification system, but not really. Uh, wasn't quite yet there. And it took us into the era of photography with astronomer Max Wolf, who would publish the initial classification system that persisted up until Hubble. And his system basically was just a bunch of cryptic letters that he would attribute to what he identified as 17 different types of non-galactic nebula, depending on, various characteristics such as how patchy they were, how well developed, how spirally they were, and so on. This is a example of what uh, many astronomer some sketches taken off of the Leviathan telescope in Ireland, showing just the general distribution. This was published around in 1880, so just slightly at the cusp of the era of photography. Uh, and so we briefly left off. We exit uh, the pre-Hubble era with what became known as the Max Wolf system of the 17 cryptic letters. And we move on into Hubble, where his claim to fame that many of us recognize him for was establishing that the universe was expanding. Uh, but as prior to this, he was working on his PhD dissertation at Mount Wilson Observatory, and he was studying galaxies. And in 1926, he published uh, his work on extragalactic nebula, which was the precursor to a work in 1936 that actually spelled out his classification system in full. And over the next preceding 10 years, he would go on to refine this initial publication into the realm of nebulae. And he specifically broke down galaxies, which he helped establish as being outside of our galaxy and distinct from nebulas, into four major groups, specifically ellipticals, spirals, lenticulars, and irregular galaxies, which with irregulars being the oddball out, not really fitting into any of the preceding three classes. And to circle back onto Wolf's system, this is an actual scan taken from Hubble's PhD dissertation. And if you'll notice at the bottom, it's showing all of Wolf's classes of of nebulas, or in this case, galaxies. And we can see a lot of really familiar shapes. The top row looking very much like what we would see as elliptical galaxies, maybe, or in some cases, fuzzy face-on spirals, transitioning down into edge-on through a lot of these, and then some other more well-defined spirally types as we get closer to the bottom. His scheme was ultimately expressed as what's become known as Hubble's tuning fork, which is this diagram here. Some people may be familiar with it, and it gets its name aptly of being a tuning fork with elliptical galaxies. Let me turn on my laser pointer, being over here on the left-hand side and transitioning over into two classes of spiral galaxies, and then irregulars being over on the far right, and lenticulars are actually located here at the juncture between spirals and ellipticals, although it's not shown well on this diagram. And with that, I mean, was a good starting point. It still persists today. There's still some contention over how well this system works. It's primarily based on the visual appearances of galaxies, not based on any other characteristics such as spectra or metal or rough content in terms of metals or radioactivity that we might see in some of the subclasses that we'll talk about next time. So there is very much a subjective element to Hubble's entire classification scheme, which you can imagine astronomers don't like that. They like to have objective criteria, so that way something either is or is not, and makes their life work, but makes their research a little bit easier. And so, trying to resolve some of these conflicts, we have several works in between Hubble's classification and today, with the most notable being what's become from Gerard de Vaucluse, who published what it has become the most commonly used extension of the Hubble sequence. And as an interesting note, Vaucluse would also go on to promote the idea of galaxy superclusters, which we most prominent examples being the Virgo supercluster that we may know today. But getting back on track, he was more interested in annoyed that as certain aspects of spiral galaxies were ignored within Hubble's system, notably rings and certain dust characteristics. And like everyone else, we need to have multiple standards for everything. That was there. Ooh, I moved some things out of place there. And um, before we get on into this, we also need to make a quick segue over into what is referred to as early and late type galaxies, which, like so many things, is a bit of a misnomer. And we would think that early galaxies would refer to distance galaxies that are closer to us or farther away from us, and representative of the galaxy's age, which is somewhat true. But instead, it's referring to how much gas content and star formation is ongoing within certain galaxies. For example, spirals and irregulars are often labeled as late type galaxies since they still contain large amounts of gas to form new stars, which you would seems like an odd designation is something. But really, what this is saying is they are, oh, sorry. And sorry, I'm losing myself here. Well, ellipticals are considered early type galaxies, as they have consumed the majority of their gas. So they basically ended their star formation early on in their history versus spirals, which are still undergoing star formation late into their histories. So a little bit of confusing no there, which clearly has tripped me up when trying to re-explain it. And and this is also a little bit more confused by people associating the Hubble diagram with ellipticals representing like an evolutionary sequence, which is actually what Hubble did as well initially, where it was believed at the time that ellipticals were um, the early stage of spiral galaxies. And to circle back onto what McClure's was wanting to fix within the Hubble system here, is a feature that's commonly known as rings in galaxies. As we can see that this is um, NGC 6782, and it has a prominent central ring here around the core with two spiral arms coming off the top and the bottom in this particular image, and then a farther out ring, and there's just this very smooth zone here in the center that is lacking any real star formation outside of the arms. And so this is one of the things that McClure was wanting to sort of encapsulate in his extension. And so now we can move on to actually talking about the different galaxies that fall underneath classification Hubble's system, starting off with irregulars. And per their name, they are irregular. They lack any significant features that would allow them to be placed in the other three categories. And many of these we are currently think are actually dwarf galaxies, which are which we'll talk about next time, which are basic galaxies that are formally defined as having 1/10 the mass of the Milky Way. So these are somewhat small galaxies overall, hence their names. Some irregular galaxies may also be, in some cases, very small spiral galaxies that have been distorted by gravitational interactions with with a near galactic neighbor. Example of this might be considered M82, the Cigar Galaxy. These are separate from what are classified as peculiar galaxies, which specifically refer to galaxies that are actually which are ongoing a galactic merger. An example of a peculiar galaxy would be the antennae galaxies, for example. But we'll talk more about peculiar galaxies next time as well. From irregulars, these were broken down into two subtypes. Uh, Irregular one galaxies and irregular two galaxies. And depending on mostly separated by certain features or lack of features in some cases. So irregular one galaxies have at least some level of organizational structure, maybe left over um, certain, like, for example, the rings that we saw on the previous image of NGC 6782. But there is also may also still have some spiral structure to them, but not nearly enough, but it's been greatly distorted, or it's not nearly enough for them to be cataloged as a standalone spiral galaxy. An example of what a regular one galaxy is that has some spiral definition is the Large Magellanic Cloud, which we unfortunately can't see from the northern hemisphere, and many of us greatly bemoan this fact. And the irregular IM galaxies, which are the exact opposite of SMs, they lack any spiral structure at all. And a more prominent example of this is the Small Magellanic Cloud, which is both of those are irregulars, and they're also dwarf galaxies. And as I had mentioned, on the galaxies that may have at one point had spiral structure, but now are classified as irregulars, we have M82. There's no organizational structure that we can clearly make out with that. And so here are just some visual examples showcasing the three different types and how you can get them. So up here on the left, we have Hubble images of M82. And you can see that there's just this giant spattering mess. You don't really see any clear spiral definition, even though this disk behind it does have some sort of spiral characteristics, or at least it's in this rough ellipsoid. And so hence why it's classified as an IM, a 1M irregular galaxy. In the upper right over here, we have the Large Magellanic Cloud, which has a little bit of spiral structure to it. We have a little bit of here on the lower left and the upper right, and maybe hints of a spiral arm here. So, some level of spiral nature, but again, still classified as an irregular because it's not really prominent. It's not well defined. So hence where it's classified. And then we have the Small Magellanic Cloud here in the center, lacking any sort of spiral structure at all, and it's just a giant blob, but also relatively small, and so it's classified as a 1M instead of a 1SM. From irregulars, we move on to ellipticals, and as their name would first suggest, these are basically just blobs of galactic blobs. They're most prominently defined by just this giant ellipsoid. There's no shape or other texture to them, and they're primarily cataloged by just how circular or deformed the ellipsoid is. Ellipticals are typically found near the center of galaxy clusters, primarily due to the process in which these galaxies form, and they possess very little star formation and are generally contain old low mass stars. And briefly mentioned earlier that Hubble originally proposed that ellipticals would evolve into spiral galaxies over the course of their lives. And we now know that the actually opposite is true. And elliptical galaxies are actually created by the merger of two galaxies, not necessarily two spiral galaxies. For example, one elliptical galaxy can merge with another spiral galaxy, and you still get an elliptical galaxy out of that. Um, This merger process is probably why we'll see them in the center of galaxy clusters. You need to have two galaxies in close proximity to merge. And the center of galaxy clusters have plenty of these. And this also contributes, this repeated merger or multiple mergers that some ellipticals may have undergone is the reason why these are usually the most massive galaxies that we observe. For example, the famed galaxy Messier 87 which we have photographed the center black hole of, is a very massive galaxy with its central black hole alone being, I think, 2 billion solar masses off the top of my head, compared to the 2 million solar masses found in our own supermassive black hole here in the Milky Way. So, as part of his catalog scheme, Hubble set about, he just labeled them based on how elongated the galaxy is using numbers from 0 to 7. Very unoriginal, but it works. An E0 galaxy is a mostly spherical elliptical galaxy, while an E7 is one that is highly elongated or stretched. And as I mentioned, Hubble's system is very much visual based. It's what's known as a morphology system, which it's describing the physical appearance of something. And this means that his system is biased in many ways, including how the galaxy is actually positioned from our point of view. And there are times where certain galaxies will be misclassified. For example, in 1966, we determined that some ellipticals that were classified as E4 or E to E7 elliptical galaxies were in fact lenticular galaxies. So there is plenty of room for error in the system, which is another reason why it's not it has its flaws. Let's just say that. So here are some examples on the two extreme ends of the spectrum. We're bringing up Messier 87 here again. It is a clearly defined, basically near circular galaxy, elliptical galaxy, with the exception of this jet, which is only visible in very long exposures. Uh, so hence the E0 classification. And then over here on the right, we have NGC 4623, which is clearly very elongated, has this long ellipsoidal shape, hence the E7 designation. Questions before I move on? I think I might be moving a bit too quickly here. I want to make sure I'm not missing out on anything.
Hey, Connor, just quick one. When Hubble started this classification, when he said extra galactic, was he thinking just outside of the plane of the Milky Way, or did he, at that point in time, you would think he would have known about, the distance that even some of those that you could see through the Milky Way were actually really way far away.
So the galactic versus extra galactic designation actually predates Hubble when they didn't know
Mhm.
when they only had the one galaxy to search from. And keep in mind that with Hubble's work, it was still very much in its early stages at the time. And although there was the assumption with him that many spiral galaxies were then, outside of our galaxy, or spiral nebulas, excuse me, um, it would take many more years for precise distances to many of these galaxies to be known and to actually sort out whether or not they were truly outside. Certain ones were truly outside of our galactic neighborhood, or if they were inside. Though in many cases they were.
Okay, thanks.
Uh, so moving on into the next class of Hubble system, we arrive at lenticulars, which are the midpoint between elliptical galaxies and spiral galaxies. And there are a lot of shared characteristics between the two, but predominantly what's separating these from ellipticals as its own separate class is that they will have a well-defined galactic disk, unlike the fuzzy ball that you'll find with most ellipticals, as also as a central bulge or core region. And some of them will also have bars, which are lanes of gas and dust that extend out like a twisty top from the galactic core itself. However, they do not have spiral arms, which is what's or other spirally type structure, which is what separates them out between spiral galaxies. And in fact, this lack of spiral structure uh, can be an issue where lenticulars, when viewed edge on, may not even be distinguishable from what you would expect of a spiral galaxy. And so there are certainly instances where a galaxy has been misclassified as a spiral or vice versa as a lenticular. But this is also true of some face-on lenticular galaxies, where they might be classified as an elliptical. Again, they're straddling this midpoint between spirals and ellipticals. And depending on how well the galactic disk itself appears in the photograph or eyepiece that is being observed at. Okay, come on, next slide. Next slide. There we go. So here is a prototypical example of a lenticular galaxy. This is NGC 4921. Uh, you'll kind of see that this has some spirally type structure. We have a little bit of swirling here on the right-hand side. We also have this ring system that McClures was interested in trying to separate out, and a little bit more of some sort of spirally definition, but they're not really prominent arms. So it's almost like these outer regions of the galaxy are just being dragged along as one uniform mass rather than as different arm type structures. And so well, this is one example of why we classify them as a lenticular galaxy. We also don't have any clear bars as an example. So there's not, as I mentioned, some of them will have bars and some will not, which is a characteristic shared by spiral galaxies to a certain extent. Some other characteristics of lenticular galaxies is that they share low star formation rates. They don't have the prominent dense gas regions that you would find in spirals. Uh, Drawing a distinction here with gas over dust, which is uh, basically uh, material that's left over in the galaxy that doesn't contribute to star formation, which they could be just regions of nebulosity that are too diffuse to collapse to form new stars. Uh, they also have a significant population of old stars relative to spiral galaxies, well, which means that they would placing them closer towards ellipticals in that old to new star ratio. And they are classified out between whether or not the lenticular galaxy contains a bar or does not as a primary categorization unit, and are further classified out based on the relative amount of dust or the inert stuff that is no longer forming new stars, with one being this lenticular galaxy that contains lots of dust, and three being one that contains minimal dust. So here are some examples. On the left, we have NGC 4459, which is a galaxy that is, um, may have had a typo in that first slide. I did. That should be reversed. So is an S3 galaxy. It has lots of dust. I apologize for that typo oversight on my part. And over here on the right, we have NGC 2101, which is an S01 galaxy, which is one that has minimal dust. Wait a second. I may have confused myself there on my own definition. So dust is being stuff that does not form stars. So even though this galaxy here looks like it should be an S01, this dust here is likely contributing to star formation within the galaxy. So it's not necessarily inert, which is why it's an S3. Versus over here, this has a lot of dust, but no active star formation, even though it looks like so it's very much an optical illusion here on this whole dust versus gas debate. Can just more confusion to our already confused system of galaxies. So next we have to ask ourselves, how did lenticulars form? Are they one option that has been proposed is that these are faded spiral galaxies that have used up all of their gas and star formation, with the spiral arms dissipating over time or being disrupted by near passes with other galaxies, with other galactic neighbors close to them, which the main evidence driving this is the low gas content and low star formation rates within the galaxy. The other option is that lenticulars are actually the result of galactic mergers between a dwarf galaxy that has merged with a larger parent galaxy. This uh, requires that the dwarf galaxy is one that's small relative to the parent, so you don't wind up with uh, merging into an elliptical galaxy, but still large enough that it's going to disrupt the star formation itself. So it's possible that the small or large Magellanic Cloud, when they merge with the Milky Way, will reclassify the Milky Way as a lenticular galaxy. These are both relatively small overall. And the main piece of evidence that drives this particular hypothesis is how much larger the central bulges of lenticular galaxies are with respect to spirals. And in likelihood, both of these are likely correct. It's rare in astronomy that any single one theory of how something forms is correct, and usually multiples. A key example of this is supernovas, in that there are like 14 different ways that a supernova can occur. So, and from there, we move on to our last classification, the very vast and diverse spiral galaxies, which are the most common out of the four types that were classified by Hubble. With 60% of all of the galaxies, large galaxies that we observe, these are galaxies that aren't dwarf galaxies, mind you, uh, are in fact spirals, compared to 20% for ellipticals, and evenly split between 10% or and then the remaining 20% is split somehow between irregular galaxies and lenticular galaxies. So very much the latter two not being nearly as common. Um, yeah, as it's been mentioned, one of the main things that people didn't like about Hubble's system was that it didn't really, there's just so much variety to spirals that that it just doesn't, it lacks a lot of ability to separate out these details that might be of interest to certain types of professional astronomers. So we wind up, this was a slide that was supposed to appear earlier. And this is just complaining about how people like to make lots of standards and then you don't know which standard's the correct one to use. Like, for example, all of the different ways that we have classified stars and now galaxies. Hmm. And so, circling back to de Vaucluse, who I mentioned earlier, this ultimately is what he came up with when he wanted to augment Hubble's system. He added this center third bar here of intermediate spirals. And we still see all the other elements were named. This one also includes lenticular galaxies to better place them, which we missed from that earlier diagram. So we have all the ellipticals, the irregulars, the three main types of spirals: barred spirals, unbarred spirals, and intermediate spirals, and then irregulars and dwarf galaxies over here on the right. Well, certain types of dwarf galaxies. So with that, with the core system, we have three clear designations, primary designations for spiral galaxies. As I mentioned, they are the unbarred spiral, the intermediate spiral, and the barred spiral. Uh, each with their own distinct designations with SA, SAB, and SB, respectively. There is an additional lowercase added to this classification system that is used to designate how similar to a spiral galaxy is to an elliptical, which is a little bit confusing. Why are we comparing spirals to ellipticals? But that's what's there. With well, an example being an SB lowercase a is more elliptical than an SBC galaxy. Another characteristic that's designated by the lowercase letter is how hard to separate the spiral arms are between an individual spiral galaxy. With A being less defined spiral nature, but you can still clearly see it, and C being very prominent spirals. So putting this into visuals, we have on the left NGC 2841. This is an SAA spiral galaxy. So we can see that this the elliptical nature, the lowercase a, is both referring to the lack of spiral arms, but also the inclination of this galaxy, which is sort of tilted edge on to us and maybe inclined a little bit, makes it look more like an ellipsoid here rather than a perfect spiral, like you would perhaps see in the Pinwheel Galaxy in Messier 101. And then on the right, we have NGC 3430, which is an SAB. So this is an intermediate spiral galaxy that has clear spiral structure with well-defined arms here, and also is mostly face on. So it is getting the C because it is closer to a sphere than over here on the left. So some characteristics that are shared across all spirals is they have a central bulge or core region, which is primarily contains old stars that are orbiting around the galaxy's parent black hole. There are as many, at least two spiral arms, which sometimes more. I think the most I was able to find was a spiral galaxy that had six spiral arms to it. And there is also a well-defined halo region, which is a region of stars that are floating above and below the galactic disk, forming just a general diffuse cloud. And that has a very sparse star population compared to the galactic disk itself, and the significantly higher rates of star formation than you will find in ellipticals and lenticular galaxies. But going, so those are the characteristics that are shared by all three subclasses of spiral galaxies. We now move on to what separates out barred spirals. And these are the most common class of spiral galaxy. And it is currently believed, depending on how recently you access the news or Google search results wants to tell you, is what we currently think the Milky Way is. We think it is a barred spiral galaxy with three arms, possibly four, but we aren't quite sure on the fourth. It's hard to see through the other side of our galaxy. The bars get their name because there is very prominent spikes extending out of the core that connect to two of the spiral arms. Generally, there is only there's two bars. There's not a bar for each individual arm in the galaxy. And this bar itself serves an interesting purpose. It actually is funneling gas in from the galaxy's exterior towards the galactic core and forming new stars in this dense region of material as it migrates in. We currently think that the bar itself is a sign of how mature a galaxy is, with young galaxies lacking much of a barred structure, because which we see from spiral galaxies that are farther away from us, and barred spiral galaxies, and spiral galaxies closer to us, generally having this bar structure, uh, which because they are closer to us and thus older in the age of the overall universe. Right, good friend, the speed of light, making fun of us again. So this is an artist's rendition of what we think the Milky Way might look like if we were somehow able to view it from edge on, largely based on what we've been able to gather from radio astronomy. And we can see that there are, several, we have at least two major arms. We have the Perseus arm and the Centaurus arm, but also some other minor diffuse arms here, like here in the outer arm. And so for some reason, these are only classified as major arms. So it's not like we consider the Milky Way to have six spiral arms like we would have here, 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 and here. Well, that's four. depending on how you want to count it. So there's is some debate still about exactly how many spiral arms are within our galaxy, and this is, as I said, speculation. This image is an approximation of what we think it looks like. So from barred spirals, we get into intermediate spirals, which are the midpoint between a barred and unbarred spiral. It may possess some level of a bar structure, but if it is there, it's very diffuse compared to a barred spiral. And I forgot to point this out earlier. So these structures here coming off the galactic core are what we refer to as bars. Should have pointed that out. Sorry about that. So an example that we might find with an intermediate spiral galaxy is Messier 83, very prominent galaxy in the springtime, which is classified as an SABC. So looking at this designation, it is an intermediate spiral galaxy with a very circular shape, hence the C designation. You can see that there is kind of a bit of a bar here and here, but the overall activity within the galaxy makes it, excuse me, not clear, makes it a diffuse and not nearly as well defined as you might see in some other barred galaxies. Hence its place as an intermediate. And some of this is slightly out of order. I'm missing unbarred spirals here. 1 second. Let me see if I. Oh, I completely missed unbarred spirals. I thought I was missing something. Well, okay. So I missed the whole entire section when putting this presentation together. I apologize. So, uh, grand design spiral galaxies, skipping over unbarred spirals because I forgot to put them in here. Um, these are this is a moniker that's been primarily attributed to C subtype spiral galaxies, and it's given to spiral galaxies that have very well formed spiral arms and a very large amount of organization. These galaxies, grand design spiral galaxies, can be both barred or unbarred, and is that a term that originated in a 1966 paper that was studying how the spiral arms were able to maintain their shape. And even, there is currently debate about if we know the Milky Way is a spiral type, but we don't know if it is a grand design type spiral. On the opposite end of grand design spiral galaxies, we have flocculent galaxies, which is a term simply itself meaning flaky. So these lack a well-defined organizational structure. So they're the exact opposite end of grand designs. We aren't quite sure on the mechanisms that result in the formation between the two types. And we currently think that a mechanism known as density wave theory is what's the main driver behind the well-formed structure that we see in a grand design spiral galaxy. I won't be going into density wave theory. It's a little bit like, and so to finishing this up here, we have two examples of a flocculent and a grand design spiral galaxy. On the left is NUC 2775 is an example of a flocculent. So we have there's no real strong spiral arms, although there is still some spiral structure here versus the grand design nature, which I wasn't which the image makes it look like there isn't a lot of spiral organization, which is a little bit misleading. But the SCA 81 is classified as a grand design spiral galaxy with this upper arm here, with arm here extending from the top to the bottom, and the reverse arm at the top from the bottom to the top. And that ends the first part of my presentation for galaxy classification. I will have to revisit unbarred spiral galaxies next time. Any questions or comments? Oh, and the 4.5 pages of references that went into finding all of this.
Yeah.
Yes, Tom.
Hey, Connor, a couple of things. First of all, my recollection of to flocculate means to sort of pull together or aggregate. So flaky would apply, but does that kind of mean that they're in the process of being somehow aggregated or being pulled together somehow or something like that?
That
I'm
is a good
trying to figure
question,
out.
and I do not know the answer to that. I know it's just a general designation that describes the appearance, but I don't know whether
Yeah.
it's attributed, if they've tied that designation back to a formation process in specific that separates the two
Oh,
types.
okay. Um, the other question is, I sort of recall dark matter was, I don't know, invented among other things to help explain spiral galaxy rotation, how the spiral arms sort of stay together instead of all twisting
It's
together.
it's not
Um,
necessarily attributed to spiral galaxies, although that is one of the main supporting things. But it's basically dark matter is attributed to how the entire galaxy or any galaxy maintains its shape because all of the galaxies farther out from the central core would be under less gravitational influence, and so should on any galaxy decide to just fly apart. And so dark matter is just the main amount of mass that allows those outer stars in order to maintain the structure of the galaxy itself. So it's not just spiral galaxies that are the driving decision, are one of the main supporting
yeah,
visual observations behind dark matter.
I think I associate it with that because I think that's the first place I
It is
uh,
it is
heard
certainly the
about it.
first place that it was first observed in terms of like why do these galaxies not fly apart in specifically in spirals.
So that leads me to the question of the barred spirals. Do they maintain that bar as well because of perhaps dark matter, or do they slowly become, I forgot what you said, the intermediate sort of the one where the bars are bent a little bit?
That that is a good question and one I did not think to look up while presenting this. So I do not know the answer to that one either. That is a very good question, Tom.
Thanks. Yeah, that's it. It's always my goal to ask a question that that gets a good question.
No, those were very good questions. It's
Thanks,
not
Connor.
often I get a question asked where I don't know the answer or Doug doesn't know the answer to. So, and with that, uh, Doug, I think you're up next. If you are ready, you
Yeah.
should have co-host permission. So share whenever you're ready. And I'm going to go get water to wet my throat.
Oh, can everybody see that all right? Hello?
Can you hear me? Yeah, we
Yes,
can
we
see
can
you.
see it.
Okay. So I'm going to talk about a very well-known astronomer, Harlow Shapley. Um, this particular picture that I'm starting with, some months ago, I did a presentation on a mural that was painted called Man in the Universe. Um, I just thought this would be a good place to start. He's in this mural. That's him. He's in the inside the yellow dotted line circle. And I'll talk about what's going on in this picture, even though we're not talking about the mural here, but I'll spend a couple minutes on it. For those of you who missed that presentation, I might give it again someday.
I believe that
Uh,
presentation is archived on our YouTube channel, if those
yeah,
who do not want to wait for that.
for anybody who doesn't want to wait. So critical details, this is the boring stuff. He was born November 2nd, 1885 in the town Nashville, not Tennessee, Missouri. He died not too long ago. Well, I guess actually about 45 years ago or so. October 20th, 1972, Boulder, Colorado. He graduated from the University of Missouri with his undergrad. He did his grad work at Princeton. He was married to Martha Betts. Uh, that's her down at the bottom right there. She was an astronomer herself, so astronomy ran in the family. They had 5 children, which 3 of them went on to be very successful careers and famous in their own right. Mildred Matthews, the daughter, became a famous editor and writer. Lloyd Shapley became a mathematician and economist, and he won the Nobel Memorial Prize in Economics in 2012. And Willis Shapley became a senior executive at NASA. All right. Um, his education, he never got beyond elementary school. He did his elementary school at Jasper, Missouri, but then he took off and worked as a journalist. He studied at home, covering crime stories as a newspaper reporter for the Daily Sun in some town called Chanute, Kansas, and published some stories for the Times of Joplin, Missouri. In Chanute, he found a Carnegie Library, started reading and studying on his own. He returned back to high school and finished a 6-year high school program, and he did it in a year and a half, graduating as the class valedictorian. Smart person. In 1907, Shapley went to the University of Missouri to study journalism. He had no intentions of studying astronomy. He wanted to be a journalist. But then when he learned that the School of Journalism at the University of Missouri had not opened yet and would not open for 1 year, he decided to study the first subject that he came across in the course directory. The first subject was actually archaeology, but Shapley later says he couldn't pronounce the word properly, so he turned to the next page, which was astronomy. How's that for picking a major? Um, so after he graduated with his undergrad work, he received a fellowship to Princeton for his graduate work. He studied under Henry Russell. I believe we did a presentation on Russell, didn't we? Connor?
Sorry, Mike's muted. I do not think we've done a Russell.
Oh, okay. All right.
Do you want me to add him to the list of people we should look at some point in the future?
Well, I mean, I know I've heard of him.
I don't think I
So
have.
anyway, Shapley would use the period Laminosity relation for Cepheid variable stars, which we all know was discovered by Henrietta Leavitt. He used that to measure the distance to globular clusters. He was very instrumental in moving astronomy away from the idea that Cepheids were spectroscopic binaries and were actually pulsating stars. Based on those measurements, he realized that the Milky Way galaxy was far larger than anyone had previously believed. And he determined that the sun's place within the Milky Way was in a fairly nondescript location out towards the edge. He was the first one to who came up with that idea and supported it. So this goes along with the idea of Copernicus that the Earth is not at the center of the universe, it's not at the center of the solar system, and it's not at the center of our galaxy. So he was important in those lines. This is probably what he's most well known for. It's called the Great Debate. So it's also called the Shapley-Curtis debate. April 26, 1920, at the Museum of Natural History in Washington, the astronomers Harlow Shapley and Heber Curtis had a debate, basically, about the nature of spiral nebula, which we just talked about in Connor's presentation, and the size of the universe. Harlow Shapley believed that those nebula, spiral nebula, were small and were actually part of the Milky Way galaxy. That's because he had measured how large the galaxy was, but we had no way yet of measuring the distances to the other galaxies, so he assumed that everything that you were looking at was part of the Milky Way. Curtis, of course, was on the other side. He believed that all of those other spiral nebula were independent galaxies. They were exceedingly large in distance. The two scientists, Shapley and Curtis, both presented technical papers about the scale of the universe during the day, and then took part in a joint discussion in the evening. Much of the lore of this great debate grew out of the two papers that were published by Shapley and Curtis in the May 1921 issue of Bulletin of the National Research Council. The published papers each included counter-arguments to the position advocated by the other scientists, along with the arguments supporting their own position. I've never read these papers. They might be fun to read. So there's Curtis down in the middle, and Harlow Shapley's on the left, and Spiral Nebula in Andromeda. So the point of the arguments went according along these kinds of lines. Shapley basically presented the case the Milky Way is the everything. It's the entirety of the universe. He argued that spiral nebula, such as Andromeda, were part of the Milky Way. He backed up the claim by appealing to their relative sizes. He said if Andromeda was not part of the Milky Way, then its distance must be on the order of like 10 to the 8 light years or something, some really large distance, which he said most contemporary astronomers did not want to accept that kind of a distance for nebulas. Shapley also relied heavily on the work of an astronomer called Adrian von Manen, a very well-respected astronomer. Von Manen had claimed that he had actually observed the Pinwheel galaxy rotating, and that if the Pinwheel galaxy were in fact a distant galaxy and could be observed to be rotating on a time scale of years, then the orbital velocities would have to be enormous, and there would be a violation of the speed of light in vacuum, which would be a really severe problem with physics at this time. So Shapley also backed up his claims with observations of nova in the Andromeda Nebula that he said had briefly outshone the entire nebula, constituting what he thought was an impossible output of energy. So those were his arguments that Andromeda was not a separate galaxy. Curtis, on the other hand, contended that Andromeda and the other such nebula were separate galaxies or island universes, as he liked to use a term that had been put out by a philosopher a couple hundred years earlier. He showed that there were more nova in Andromeda than in the Milky Way. Based on that, he would ask the question, why would there be more nova in this small section of the Milky Way than other sections of the galaxy, if Andromeda were not a separate galaxy? This led to the idea that Andromeda was a separate galaxy with its own age and rate of nova occurrence. Curtis also noted that there were large radial velocities of spiral nebula that suggested that they could not be gravitationally bound to the Milky Way. And he also noted there were dark lanes present in other galaxies that was similar to the dust clouds found in the Milky Way. So these were the kind of arguments that went back and forth throughout this great debate. We all know who was right and who was wrong. Um, Later in the 1920s, Hubble showed that Andromeda was far outside the Milky Way by measuring the Cepheid variable stars, proving that Curtis was correct. We now know that the Milky Way is one of only something like 10 to the 12th galaxies in the observable universe. Um, Astronomers have generally accepted the idea that the nova that Shapley referred to in his arguments were in fact supernova in Andromeda, which they do indeed outshine the rest of the galaxy for a short amount of time. On some of the other points that were brought out in the debate, there were mixed results. For example, the actual size of the Milky Way is somewhere between what Harlow Shapley thought and what Curtis thought. Um, and Shapley had one point right. He believed that the sun was out near the edge of the Milky Way, which it is, whereas in Curtis's model, Curtis had the sun very close to the center. So, this kind of stuff went back and forth. And it later became apparent that von Meyen's observations of the rotation of the pinwheel galaxy were just plain incorrect. You can't see the rotation of a galaxy in a human lifespan. So that's Hubble down in the middle. And I love that picture on the right. That's one of my favorite pictures of Hubble. He's sitting at the prime focus of the 200-inch telescope at Mount Palomar. Um, After the debate, at the time of the debate, Shapley was working at Mount Wilson Observatory, where he had been hired by George Ellery Hale. Um, After the debate, he was hired to replace Pickering, Charles Pickering, as the director of the Harvard College Observatory. Shapley would serve as director of the Harvard College Observatory from 1921 until his retirement in 1952. During that time, he hired Cecilia Payne, who I know I talked about when I did my lecture on women or Pickering's harem stuff. She would go on. She would be the first woman to get a PhD in astronomy from Harvard. Actually, Harvard set up a separate college just for women called Radcliffe College. And she was the first woman to get a PhD from Radcliffe for the work that she did at Harvard Observatory. Harvard Shapley was made director emeritus and Payne professor of astronomy at Harvard in 1952 when he retired. The designation of Payne Professor of Astronomy is a very honorary designation. It's like almost the highest honor Harvard can give to a professor, is a Payne Professor, it's called. In 1953, he proposed the idea of what he called the liquid water belt theory, which we now know of today as what's called the habitable zone. And this is the idea that for a planet to have life, it has to be in a certain, whatever you want to call it, Goldilocks zone around its star, where it's not too hot, not too cold. He actually came up with this idea as far back as 1953. 1935, while he was still director at Harvard, he made the cover of Time magazine for a lot of his work on galaxies. That's something astronomers rarely do, is make the cover of Time. There's the cover of Time with his picture on it.
So also on Cecilia Payne, she was our featured astronomer last month. And if you're
Oh,
interested
okay.
in her,
I wasn't
you'll
sure. I
also
didn't
find
know.
her recording of that presentation on our YouTube
Okay.
channel as well.
I know I had talked about her in my thing on the women that under Pickering. Shapley initially opposed a lot of what Hubble did. He actually critiqued Hubble and at one time regarded his work as junk science, but he received a letter from Hubble showing where Hubble went and displayed the observed light curve of a Cepheid variable in the Andromeda Galaxy, and that turned him around. He withdrew his criticism of Hubble. He reportedly told a colleague, "Here is the letter that destroyed my universe." He also encouraged Hubble to write a paper for a joint meeting at the American Astronomical Society and the American Association for the Advancement of Science. Obviously, Hubble's findings went on to reshape our view of the universe. Despite having earlier argued against the idea of galaxies other than our Milky Way, Shapley went on to make significant progress in the research of the distribution of galaxies, working between 1925 and 1932. In that time period, while he was at Harvard, he worked to map over 76,000 galaxies. He was one of the first astronomers to believe in the existence of galaxy superclusters. Shapley later discovered a large and distant example, which was later named the Shapley supercluster. He estimated the distance of this supercluster at 231 megaparsecs, which is within 15% of the currently accepted value. That's a picture of the Shapley supercluster there.
For those who can't do conversions in their head, that's around 700 billion light years.
Yeah, sorry. In the 1940s, Shapley was also a big activist in a lot of different causes. In the 1940s, he found government-funded scientific associations, including the National Science Foundation. He's one of the original founding people who helped create National Science Foundation. He also shares credit with the British biochemist Joseph Needham for the addition of the S in the UNESCO, United Nations Educational, Scientific, and Cultural Organization. The S is scientific, and he was very heavily responsible for getting that included. His activism also included membership in a group called the Independent Citizens Committee of the Arts, Sciences, and Professions, ICAS, which was heavily involved in politics, actually. On November 14, 1946, Shapley actually appeared in front of the House Committee on Un-American Activities. Remember them? For his role as a member of the ICASP. The House Committee described the ICASP as a major political armor of the Russophile left. Ha ha. But Shapley clearly told them what to do with themselves in no uncertain terms. At his testimony in front of the House Committee, he was very blunt. John Rankin, who was the chairman of the committee, said, quote, "I've never seen a witness treat a committee with more contempt and considered contempt of Congress charges." Shapley accused the House Committee of Gestapo methods and advocated for its abolition, saying that it had made civic cowards of many citizens, etc. That picture on the right is a picture of some ICAS members in October 1944. There's FDR sitting down at the desk, and Shapley is standing on the right there, on the far right. A few weeks later, in early 1947, Shapley became the president of the American Association for the Advancement of Science. This was a clear rebuke of the House Committee on Un-American Activities from the American Association of Advancement of Science. They literally, again, like I said, told the committee, go jump in the lake. Number of awards have been awarded to Harlow Shapley over the years. Member of the American Academy of Arts and Sciences, American Philosophical Society member, member of the National Academy of Sciences. He received the Henry Draper Medal from the National Academy of Sciences. He received the Prix Jules Janson of the Société Astronomique de France from the French Astronomical Society. Rumford Prize from the American Academy of Arts and Sciences in 33. Gold medal from the Royal Astronomical Society in 34. Bruce Medal of the Astronomical Society of the Pacific in 1939. Janssen Medal from the French Academy of Sciences, 1940. Pius 11 Medal, 1941. Franklin Medal, 45. And there's a series of lectures, the Henry Norris Russell Lectureship of the American Astronomical Society. Yeah. He's got a crater on the moon named after him, got an asteroid named after him. There's that supercluster that's named after him. And he's got a visiting lectureships in astronomy from the American Astronomy Society are named after him. He's also given credit for starting the phrase better dead than red. That was a phrase that was very popular during the McCarthyism period in the 50s. In 1947, Harlow Shapley said, "Peace or pieces, a slave world is not worth preserving. Better to be lifeless like the cold moon or primitively vegetal like desolate Mars than be a planet populated by social robots." So interesting. Prolific author, wrote a number of books on a number of subjects, not just about astronomy, but a whole variety of different things. We have some of these books are in our library. 3 of them, the ones marked in red, are in our library. I read the Galaxies book a long time ago. I haven't read any of these other books. I might grab one and take a read. My summary, and this is based on what I read from other people, but partly my own. Clearly, Harlow Shapley was a brilliant person, very brilliant mind. Many astronomers and not just astronomers, but Nobel laureates and other people consider him one of the most brilliant minds of the 20th century. Some actually compare his intellectual prowess to Einstein. While he was proven wrong during the Great Debate, even geniuses get it wrong. Unlike most people, he immediately accepted his error and embraced the new reality of galaxies and the immensity of the universe. And he went on to make many groundbreaking discoveries about galaxies and their structure during his career. And unlike a lot of scientists at the time, he chose to get involved in a number of activities, activism and stuff outside of science, with very little regard to the consequences. Personal note, because I love that mural that Don Cohen did, Man in the Universe. In that mural, there are only 5 people from the 20th century shown in the mural. All 5 of them are in this little piece. This is just a piece of the mural. Harlow Shapley is on the far right, the middle figure from top to bottom. The top figure is Edwin Hubble. Then Harlow Shapley's beneath Hubble. And then the bottom figure down in the lower right corner is Curtis, the guy that Shapley had to debate with. Over on the left, you all recognize Einstein. And the figure in the middle wearing the green dress is Henrietta Leavitt. And those are the only 5 people from the 20th century that are included in this mural, which I find fascinating, of their choice. Any questions? Comments? Nothing.
Hey, Doug, he's apparently credited with finding where the center of the galaxy, the Milky Way galaxy is, and that the sun is not in the center. Do we know how he did that? Did he also find the center, like, you know, where, what is it, Sagittarius A is?
No,
Uh,
he is not credited with finding the center of the universe. He is credited, though, with determining that the sun is not at the center of the galaxy. But he is not credited with locating the exact center of the galaxy
okay,
or finding Centaurus A or anything like that. He just used his measurements of globular cluster distribution and things like that to come to the conclusion that the sun must not be at the center of the galaxy. It must
gotcha.
be near the outer edge somewhere.
Right,
It
gotcha.
wasn't until radio astronomy got into its very deep and became a real strong part that they were able to actually map the galaxy better.
Gotcha. That concept reminds me of Douglas Adams' A Hitchhiker's Guide, where he locates the Earth as being in the uncharted backwaters of the unfashionable Western spiral arm, or something to that effect.
That's close. And for those of you who have not ever seen this mural, um, the mural is at the Tucson Convention Center, and you can go there and get a look at it.
Thank you, Doug. So for next month, I believe Stephen will be doing one of the presentations. I don't know which one yet. I need to follow up with him on it again. Um, and I will likely be doing the second one, whichever that works out to be. No ideas yet on the topics, but we'll figure that one out as we get there.
Okay, so Connor, you said the second part of your galaxy classification would be February?
Yes, if I'm thinking correctly, Stephen would be doing um, the main topic, but I don't know what it's on. Now, but I'm also speculating, so I'll have to follow up with him.
So you
But
don't want to do yours in January?
I need more time to research on
Okay.
it. There's
All right.
there's a lot of ground there, and as I had with those slides, that took me almost an hour to get through. There's a lot more between those that I need to sort out. So, and there might also be more I find. So, uh, more on what we'll do next month as I figure it out. And with that, I'm going to go ahead and end the recording here.